Hello everyone. From a long time I was thinking to make a video on MOS capacitor, and this is a part 1 on this topic. In this part we will gather some basics so that we can easily understand the MOS capacitor working and its mechanism. Though we are not going in the detail and derivation of these basics, this is how the MOS capacitor looks like. It has two terminal, gate terminal and ground terminal, and it consists of three material: metal, oxide and semiconductor. This metal will be used as an electrode, and oxide will be of very thin film around 1.5 nanometer, and oxide will be used as an insulator, and semiconductor will be the body of this MOS capacitor. And we can see that this MOS name has come from the first letter of this metal, oxide and semiconductor. But metal and oxide was in the scenario of this capacitor before 1970. After 1970, at the place of metal, people started using heavily doped polycrystalline silicon. This polycrystalline silicon can withstand very high temperature and it will not react with silicon oxide. And at the place of oxide, they started using silicon nitride. But even after replacing this metal and oxide, we are like stuck with its generic name, MOS capacitor. And this capacitor is an equilibrium device, means whatever voltage we can apply across these two terminals, the charge carrier will not pass through these two terminals or across these two terminals. And it has variable capacitance, means by changing the voltage, its capacitance value will change. And this MOS capacitor, in short, called as MOSCAP. And this MOSCAP is actually the integral component of MOSFET. And this MOSFET stands for metal oxide semiconductor field effect transistor. And this MOSCAP is not widely used semiconductor, but MOSFET is the most widely used transistor. And to understand the working of MOSFET, we need to understand the MOS capacitor. This is MOSCAP. If we will do doping by N-type impurities at this side and this side, then it will become a MOSFET, and it will have two extra terminal, source and drain. And if we will short circuit this source and drain terminal, then it will behave like a MOS capacitor. And here the body of this semiconductor will be doped by P-type impurities. Now we will see the energy band diagram of semiconductor, intrinsic semiconductor, P-type semiconductor or N-type semiconductor. This is intrinsic semiconductor and there is no doping. This is the energy band diagram of this intrinsic semiconductor, and this EV is the valence band edge, and valence band will exist below this EV, and this is conduction band edge, and conduction band will exist above this EC, and the gap between EC and EV is called as forbidden energy gap. And property of this intrinsic semiconductor is that at 0 Kelvin temperature, all the electrons will be in non-exciting state and they will stay in the valence band here. and if we will apply little amount of thermal or optical energy, then they will get excited and they will cross this forbidden energy gap. And at the absence of electrons, means there will be the vacancy of electrons, they will have the vacancy of electrons will have positive charges, and they are called as holes. Here holes will come, and these holes will be in the valence band. These electrons are in conduction band and these electrons are in valence band. These holes are in valence band, and these are the electrons, and the vacancy of electrons will have positive charge and they will be called as holes. And Fermi level of this intrinsic semiconductor will lie in middle of this forbidden energy gap. This EI is called as intrinsic Fermi level. Now we will see in the p-type semiconductor, this is right now the intrinsic semiconductor, and to make it into p-type semiconductor we need to dope it with acceptor impurities. And acceptor impurities will have the property that they will have a vacancy of electrons. So if we will apply thermal or optical energy into this intrinsic semiconductor, then electrons will get excited and they will come and sit into these vacancy, into this vacant places, and same number of holes will come into the valence band. And Fermi level of this doped p-type semiconductor, earlier in intrinsic semiconductor Fermi level was in the middle of this forbidden energy gap, but now Fermi level will shift and will come nearer to EV. This is the Fermi level of doped semiconductor, doped p-type semiconductor. And we can see that here holes will be more in number, that's why they are called as majority charge carriers, and these electrons will be less in number, so they are called as minority charge carriers. And concentration of the holes can be calculated by this formula, where P is the hole concentration, Ni is the intrinsic concentration, and EF is the Fermi level of doped semiconductor. Now in N-type we need to dope it with donor impurities, and donor impurities will have the property that they have excess electrons with respect to the intrinsic semiconductor. So if we apply thermal energy, then these electrons will cross this EC and will come into the conduction band. And in this N-type semiconductor, the Fermi level will shift nearer to EC, and if we will apply more doping, then this EF will shift more near to EC. And here electrons are more in number, so they will be the majority charge carriers and holes will be the minority charge carriers, and concentration of electrons can be calculated by this formula. As we have seen that in MOS capacitor, metal, oxide and semiconductor, three are the integral component of this capacitor. So now we will see individually its band diagram without application of any voltage. In metal has the property that there will be no forbidden energy gap will exist. So Fermi level and valence band and conduction band will be at the same level, and energy required to move an electron from the Fermi level of metal into the vacuum level is called as work function of metal. And in oxide, it is an insulator. That's why there will be a large gap between the valence band edge and the conduction band edge. And in this semiconductor, this is p-type semiconductor, and its Fermi level will be nearer to the valence band, and energy required to move an electron from its Fermi level to the vacuum level is called as work function of semiconductor. Now we will see what happens when we apply a zero voltage, means when we will short circuit this capacitor. And we have taken the word ideal for MOS capacitor, and in this ideal condition the work function of metal and semiconductor will be at the same level, and this we can see in its energy band diagram. This EF, M and EF for semiconductor is at the same level, and so Fermi level, so the work function Q phi m and Q phi s will be the same. And this is for part 1 lecture, and next part we will see what happened when we apply a voltage which will be greater than 0 or less than 0, then what will happen. And this condition, because this is because of the Fermi level of metal and semiconductor is at the same level, that's why there will be no band bending in the EC, EF and EV. They will be always straight line throughout the length of semiconductor. That's why it is called as flat band condition. And at this condition, because Fermi level and of metal and Fermi level of the semiconductor is at the same place, no charge carrier will flow, and also we have not applied any type of voltage, so there will be no charge accumulation at any places. And in next part we will see when we apply the voltage which will be positive or negative, and this is the references I have used. Thank you for listening to me. Stay healthy, stay happy. Goodbye.